Hello, this is the Test 3 review. For the test, you may use the z-score table. That's that two-page table titled A2. Use the critical z-score table, your calculator, and then a cheat sheet and any notes that you want to use. One comment here about the review problems posted on Course Compass. Some of them do not have learning aids, and they look a lot different than some of the homework problems that you've seen before. That's because those are problems that I have written myself. Most of those have multiple parts, and they're going to be very much like the test questions. Sometimes I don't like the problems that are in Course Compass, so I write my own, and those are the ones that appear on the test. So make sure that you do those review problems and be prepared to see problems like those on the test. All right, so our first topic here is the idea of random variables, and we studied two types, discrete and continuous. Discrete, the values must be of a certain type, like integers. Continuous random variables, the values don't have to be of a certain type. They can take on any value within some range. Chapter 6 and 7 we study continuous random variables. In Chapter 5 we saw discrete random variables. The first type of continuous distribution we looked at was the uniform distribution. This is about the simplest of all types. Continuous random variable has a uniform distribution if its values spread evenly over the range of possibilities. So that means that no value is any more or less likely than any other. And the example that we looked at dealt with these classes. The length of the classes were always between 50 and 52 minutes, and we saw that no one time was any more or less likely than any other. And so here is the density curve for that class length. It goes between 50 and 52. It's flat on top, has a height of 0.5. And we use that density curve to find probabilities. And the way we use that is, for instance, to find the probability that a randomly selected class lasts less than 51.5 minutes. As we go over to 51, draw a vertical line, shade to either the left or the right. In this case, we shade to the right. And then the area of that shaded region is the probability that we're interested in. So we need to find the area of that rectangle. It's width times height. The height is 0.5. The width is just the difference between 52 and 51.5, which is 0.5. So we multiply those height and width to get 0.25. So that's our probability. And that's how we use density curves to find probabilities. In the definition of a density curve, it's a graph of a continuous probability distribution. And as we just illustrated, we use that to calculate probabilities. Now, two properties that every density curve must satisfy are: number one, the total area under the curve must equal 1. That explains why the height of that density curve that we just saw is 0.5. And number two, the curve cannot fall below the x-axis. That's the x-axis is the horizontal axis. And that property has to be true because the height of a density curve gives us probabilities. Probabilities can't be negative, so you can't go below the x-axis. The second type of continuous distribution we looked at is a very important one called the standard normal distribution. Standard means that we're dealing with a mean 0, standard deviation 1. Normal means that the density curve is a bell curve. Here's a graph of our standard normal density curve. It has 0 right in the middle, and the horizontal axis is labeled z-score. Whenever we work with the standard normal distribution, we always use the variable z. Okay. The example dealing with standard normal distribution that we looked at dealt with these thermometers that are supposed to give reading of 0 at the freezing point of water, but some read a little bit low and some read a little bit high. And so we assume that they had a standard normal distribution, meaning mean 0, standard deviation 1. If we let z equal the reading of a randomly selected thermometer, we'll find the probability that that thermometer reads less than 1.58. Okay. And so we do that by sketching the density curve, go over to 1.58, draw a vertical line. We shade to the left in this case, and that area is our probability. Now we can't find that area by just multiplying width times height, because it's not a simple rectangle. Instead we use our z-score table. So here's table A2, and we go to the positive z-score table, and we read this: the first two digits of our z-score on the left hand column, the last digit is on the top. So we go down to 1.5 and over to 8, and we get the area to the left of that z-score as 0.9429. So that's our area, and that's our probability. To find the probability that z is greater than some number, say for instance negative 1.23, we go over to negative 1.23, draw a vertical line, shade to the right in this case, and the area of that shaded region is our probability. So now we go to our negative z-score table down to negative 1.2 and over to 3, and we see an area of 0.1093. Now we have to remember that that is an area to the left of the z-score. That's not what we're actually interested in. We're interested in the area to the right. But we can use the fact that the total area underneath the curve is equal to 1 to find that area to the right. So to find that area to the right, we simply have to subtract 1 minus the area to the left, and that comes out to be 0.8907. So that's our probability. Okay. The next type of continuous distribution we looked at was the non-standard normal distribution. Non-standard means that we have a mean different than 0 or a standard deviation different than 1. But normal means that we're dealing with a bell curve. So the example we looked at in class dealt with these IQ scores that are normally distributed with a mean of 100 and standard deviation of 15. So notice that this has a non-standard normal distribution. So we want to find the probability that a randomly selected adult has an IQ that's less than 130. Now this is very similar to finding the probabilities of a standard normal distribution. We just have one additional step where we have to convert the x value inside the parentheses over to a z-score. And so we use the formula given here, x minus mu divided by sigma. Again, x is the number inside the parentheses, mu is the mean given in the problem, and sigma is the standard deviation. So in this case we have 130 minus 100 divided by 15, that's equal to 2. So then the probability that we want is equal to the probability that z is less than 2. And we use z here because now we're dealing with a standard normal distribution. And so we sketch our standard normal bell curve, shade to the left of 2. We look up that area from our z-score table, and that comes out to be 0.9772. So that's our final answer, 0.9772. So not a whole lot different than a standard normal distribution, just got that one additional step. The next topic we talked about was finding percentiles. And so let's look at a couple of examples of finding percentiles. So one question we asked dealing with thermometers is 67% of thermometers read below what temperature? Now that 67%, that's a percentage or it's also a probability. And so in our standard normal bell curve, we have an area to the left of some z-score equals 0.67. We want to find that z value. So this is fundamentally different than the problems that we just saw. In the problems we just saw, we were given a z-score or an x value. We want to find the area or the probability. In this case, we're given the area, we want to find the z-score. So the way we do this is we go to our z-score table and look for a z-score with an area as close to 0.67 as possible. And in this one we see an area of exactly 0.67, and so the corresponding z-score is 0.44, and that's the number we're looking for. So that number, that temperature reading, 0.44, is called the 67th percentile of the readings, and it's denoted P sub 67 equals 0.44. Now that number 67 is a probability or a percentage. The number 0.44 is a temperature reading. So this means that about 67% of thermometers read 0.44 degrees or less at the freezing point of water. Now, dealing with a non-standard normal distribution, let's go back to the IQ scores where we have a mean of 100, standard deviation of 15. Let's find the 90th percentile. So here we had two steps. The first one is find the corresponding z-score. So we draw our standard normal bell curve. We have an area of 0.90 because we're dealing with the 90th percentile, and we want to find the corresponding z-score. So we go to our z-score table and look for an area as close to 0.90 as possible, and in this case we see an area of 0.8997. The corresponding z-score is 1.28. So that's the z-score. Second step was to convert that z-score over to an x value, which is the IQ score in this case, using this formula. X is mu plus z times sigma. And so we plug the numbers in, do the arithmetic, to get 119.2, and so that is our 90th percentile. And so what does that mean? Well, it means about 90% of people have an IQ less than 119.2. Our next topic is an extremely important theoretical and practical tool called the central limit theorem. And the central limit theorem deals with calculating probabilities of the mean of a sample. So suppose we take a random sample of size n from a population with mean mu and standard deviation sigma. Now that random sample has a sample mean. We want to calculate probabilities of that. So central limit theorem, first of all, says that x bar, that's the mean of the sample, has an approximately normal distribution. That means we can use bell curves to calculate probabilities of that. Second thing it says is that the mean of that random variable x bar is equal to mu, the population mean. And the third thing it says is that the standard deviation of x bar, the sample mean, equals sigma divided by square root of n. So using these three pieces of information, we can easily calculate probabilities of the mean of a sample. So to illustrate this, suppose we have this population of women, of heights of women, that are normally distributed with a mean of 63.6 and a standard deviation of 2.5. We want to find the probability of selecting a sample of 20 women whose mean height is greater than 72 inches. Now notice here that we're asking for the probability of the mean of a sample. Whenever we have a problem that deals with the mean of a sample, we're going to use the central limit theorem. Okay. And so the central limit theorem first tells us that x bar is normally distributed. Second, it tells us that the mean of x bar is our population mu, which is 63.6. That was given in the problem. Third thing is that the standard deviation of x bar is sigma divided by square root of n, which is 2.5 divided by square root of 20. The 2.5 was given in the problem. N was also given in the problem. That's our sample size. We do that arithmetic, which comes out to be 0.559. Okay. So we want to find the probability that x bar is greater than 72. We know that x bar is normally distributed, has a mean of 63.6, a standard deviation of 0.559. So now we're simply dealing with a non-standard normal distribution problem. And so first of all, we convert the number inside the parentheses over to z-score by subtracting the mean divided by the standard deviation. Comes out to be 15.03. And so now the probability that we want is equal to the probability that z is greater than 15.03. That's a huge z-score, and so we shade to the right of that. And we could look that up from our table. The area to the left is 0.9999, and so we subtract that from 1 to get our probability of 0.0001. So remember, whenever we're dealing with the mean of a sample, then we're using the central limit theorem. Okay. Next, in Chapter 7, we started talking about confidence intervals. First confidence interval we talked about was dealing with a sample proportion. And so we, in these confidence interval problems, we want to estimate a population proportion or a population mean. And so we go out and we collect sample data, but those sample data only give us estimates of the population proportion or mean. We want to get a measure of just how accurate that estimate is, and we do use a margin of error to do that, and then based off the margin of error we calculate a confidence interval. So to calculate a margin of error for a population proportion p, we let p hat be the sample proportion, that comes from the data. Q hat is 1 minus p hat, n is the sample size, and the margin of error E is z sub alpha divided by 2. That's the critical z-score, which comes from the z-score table. The lower right hand corner has all those critical values. We take that times the square root of p hat times q hat divided by n. Now once we get that margin of error, we calculate a confidence interval for p, which is a range of possible values for p. And it takes one of three different forms, the p hat minus e up to p hat plus e, or you can write it as p hat plus or minus e, or we can write it in interval notation like this. They all mean the same thing, it's just different ways of stating it. We usually use that first step, that first kind. However, the news media often uses the second kind. Now, confidence intervals can be calculated on your calculator. You go to the Stat Test button, and select option A for the 1 proportion z interval. X is the number of successes from the data, N is the sample size, and C level is the confidence level. Now that the calculator will give you the confidence interval, but it won't explicitly give you the margin of error. To find the margin of error from a confidence interval, we can use this simple formula. Take the upper limit minus the lower limit, divide by 2. And that's based on the idea that the overall width of the interval is twice the margin of error. Next thing we talked about is determining sample size. Whenever we start some sort of statistical study, the first thing we have to do is figure out just how many people do we need to survey. And so we can use this simple formula to determine it. N is z squared times p hat times q hat divided by e squared, where z is our critical z-score based on our desired confidence level. Capital E is the desired margin of error in decimal form. P hat is an estimate of the population proportion, and then Q hat is 1 minus P hat. So plug those numbers in, do the calculation, that gives us our sample size. Now one important thing to note here is that the population size does not matter. Our population could be several thousand, several million, several billion. It just doesn't matter. So some people think that the larger the population, the larger the sample size you need. That's not the case. Now one thing to use this formula is that we need an estimate of P. And we can get that estimate from at least 3 different sources. Number one, we can use a sample proportion from a previous study. Maybe we've already got a small sample that gave us an estimate. We can use that estimate as a starting point for a formula. Number two, we can use knowledge of the circumstances. Or number three, if unknown, just use p hat equals 0.5. Why 0.5? Well, because that's right between 0 and 1, halfway between 0 and 1. Next is interpreting a confidence interval. So for instance, in one of our examples in the notes, we calculated a 90% confidence interval for p to be 0.611 up to 0.669. A correct interpretation of that would be to say we are 90% confident that p is between 0.611 and 0.669. An incorrect interpretation of that would be to say there is a 0.9 probability that the true value of p is between 0.611 and 0.669. Now why is that incorrect? Well, because p is either in that interval or it's not. There's no probability involved. Once we calculated the confidence interval, p is either in there or it's not. There's no probability or chance involved. A correct interpretation of that meaning would be to say if we were to select many different samples and construct the corresponding confidence intervals, 90% of the intervals would actually contain the true value of p. So that confidence level of 90% refers to the process of constructing the intervals, not the intervals themselves. It means that if I did a whole bunch of different intervals, about 90% of them would contain the true value of p. Next we talked about calculating a margin of error for mu, a population mean. Again, the idea here is that we try to estimate a margin of error, or we try to estimate a mean mu with a sample mean x bar. We want some measure of its accuracy. We measure that with a margin of error, and then based off of that we calculate a confidence interval. And so here's our formula. Margin of error is E is t sub alpha divided by 2 times s divided by square root of n, where s is the sample standard deviation, n is the sample size, t sub alpha divided by 2 is the critical t value with n minus 1 degrees of freedom. That comes from table A3. And alpha, our confidence level, is the area in 2 tails. So that we get that critical t-score from this table. See at the top, area in 1 tail, area in 2 tails. We always use the area in 2 tails. And so if we're at a 95% confidence level, then the area in 2 tails is 0.05. And the degrees of freedom along the left-hand column is equal to n minus 1. So it's it's the sample size minus 1. And so you get your critical values from here. And then once we've calculated that margin of error, we can calculate a confidence interval. Take x bar minus e and x bar plus e, and mu is somewhere in between those two numbers. and it takes one of these two different forms. This can also be calculated on your calculator. Again, go to Stat, Test, choose option 8, the t-interval. X bar is the sample mean, Sx is the sample standard deviation, N is the sample size, and C level is the confidence level. So plug in those numbers and it will calculate the confidence interval for you automatically. Okay, to use this formula for calculating margin of error and a confidence interval for mu, there are certain requirements that have to be met. As we stressed throughout the semester, every formula has a set of requirements that have to be met. You can't blindly plug any set of numbers into any formula and expect to get valid results. You may get results, but they're not going to be valid unless requirements are met. And so the requirements here to calculate a margin of error for mu, number one, the sample must be random sample of the entire population. And then number two, either the sample is from a normally distributed population or n is greater than 30. So if we've got a small sample size, we may not be able to use this formula unless we have some indication that the population is normally distributed. If n is greater than 30, then it doesn't matter what the distribution of the population is. And so that led us to our next topic of assessing normality. How can we determine if this requirement that the population is normally distributed is met? And we came up with three simple criteria. First, we identified outliers. Outliers were data values that were quite a bit larger or smaller than the rest. If we had more than 2 outliers, we said that the population was not normally distributed. Number two, we constructed a histogram, and we looked for a bell curve shape. If the histogram departs dramatically from a bell curve shape, then we would say the population is not normally distributed. But sometimes with a small sample, that's kind of hard to determine whether it has a bell curve shape or not. So the third step was we constructed a normal quantile plot, which is a simple graph that allows us to determine if the population is normally distributed. And we did that on our calculator. We put the data in a list, go to Stat Plot, we selected the last type, press Zoom 9, and we get something that maybe looks like this graph on the right hand side. And the way we interpret this is we look for a straight line pattern. Basically, a straight line pattern indicates a normal distribution. Something other than a straight line pattern or some other type of pattern indicates a non-normal distribution. So again, look for straight line patterns. If it has a straight line pattern, then that's an indication the population is normally distributed. Chapter 14, we looked at this idea of control charts. A control chart is a graphical tool for determining if a process is changing over time. Now, one example we looked at was this dealing with these light bulbs where we tested each batch, found the number of defects, and the question we asked is the proportion of defects changing? Is it increasing? Is it decreasing? What's going on? And so we constructed this control chart. Now in the test we won't actually construct control charts because they're kind of time consuming. We're going to focus instead on interpreting the control chart. So with the control chart we have a dot for each data value. We have a lower control limit, an upper control limit, and a center line. And so this is what our control chart is going to look like. Okay, now we interpret this using 3 criteria. We say the process is out of statistical control if, number 1, there is a pattern, trend, or cycle that is obviously not random. Number 2, run of 8 rule. There are 8 consecutive points all above or below the center line. And then number 3, there is a point above the upper control limit or below the lower control limit. And so in this one, what we saw from the control chart is that we have kind of an increasing pattern. It's kind of steadily going upwards as we go from left to right. So that is a non-random pattern, and so we would conclude that it is out of control. And in fact, we would conclude that the proportion of defects appears to be increasing. And because it's increasing, that means some sort of corrective action needs to be taken. Maybe our manufacturing machine is broken or something's going wrong. Now, if the proportion were decreasing, it would still be out of control, but that would actually be a good thing because we want fewer defects. And so just being out of control in and of itself does not mean that something is bad. Alright, the last topic here comes from section 6.6, and that's where we approximated the binomial distribution with the normal distribution. And the idea here is that we approximate those binomial probabilities by finding appropriate areas underneath underneath a bell curve. And so, for instance, to find the probability that x equaled some number like 120, here x was the number of successes, we found the area underneath the bell curve between 119.5 and 120.5. So we subtracted a half and added a half and found the area underneath that bell curve. Now that bell curve has a mean of NP and a standard deviation of square root of NPQ. And the second example, we found the probability that x was less than or equal to 120, and so we added a half and found the area to the left. Third example, we found the probability that x was greater than or equal to 121, so we subtracted a half and found the area to the right. Now this idea of adding or subtracting a half is what's generically known as a continuity correction. And so you should be able to apply these ideas to find to approximate binomial probabilities.